So, you're watching this video right now. The screen you're looking at displays millions of pixels. The thing making this possible is the Graphics Processing Unit, or GPU. It's quietly become one of the most important pieces of technology in the world. The same hardware designed to render fantasy landscapes is now at the heart of a technological revolution. AI, art, medicine, they all run on GPUs. Not just one or two, but massive farms of them. These aren't just graphics cards anymore, they are the engines of artificial intelligence. Today we're diving deep into why. How did GPUs designed for pushing pixels become key to unlocking AI? Unlike CPUs, GPUs use parallel processing. Imagine a CPU as one master chef, and a GPU as an army of cooks. This ability to do many simple tasks simultaneously made GPUs perfect for graphics. Turns out AI training also involves millions of simple calculations. Researchers realized GPUs could dramatically speed up AI training. This realization changed everything. Suddenly, training an AI model, which might have taken months or even years on a traditional CPU, could be done in a matter of days or weeks on GPUs. This wasn't just a small improvement, it was a breakthrough that unlocked the potential of modern AI. It made complex models like the ones behind ChatGPT, Midjourney, and self-driving cars practical to build and train. The AI boom we are living through right now simply would not have happened without the GPU. It is the secret engine, the unsung hero working behind the scenes. Every time you ask a smart assistant a question, get a movie recommendation, or use translation software, you are tapping into the power of a massive GPU cluster somewhere in a data center. These AI systems are built on what are called neural networks, which are inspired by the human brain. And just like the brain has billions of neurons firing in parallel, these artificial neural networks have millions of calculations that are best performed in parallel. The GPU's architecture is almost perfectly suited for this kind of work, making it the default hardware for the AI industry. The demand for these chips has exploded. Companies are now spending billions of dollars to acquire as many high-performance GPUs as they can get their hands on. It has created a new kind of gold rush, but instead of digging for precious metal, tech giants are racing to build the biggest and most powerful AI supercomputers. The company that has the most computational power, the most GPUs, has a massive advantage in building the next generation of intelligent systems. This has turned GPU manufacturers into some of the most valuable companies in the world. So, in this video, we're going to pull back the curtain on this incredible technology. We'll look at where it came from, how it's fundamentally different from a CPU, and exactly how its unique architecture made it the perfect tool for the AI revolution. By the end, you'll understand that the GPU is no longer just about making games look pretty. It's about building the future. It's the hardware that will power the next decade of innovation, and we're just getting started. So let's get into it. Let's rewind. Before RGB graphics cards, before photorealistic games, before GPUs. In the early days, graphics were basic. The CPU did everything, from running the system to putting every dot on the screen. This was an immense burden. Graphics were slow and simple, blocky text and a handful of colors. Games like Pong were revolutionary but pushed the limits of the CPU. Every pixel was a calculation, creating a bottleneck. This affected everything, even early graphical interfaces. Engineers knew the CPU was being held back. The dream was richer, faster visuals. They needed to offload graphics processing from the CPU. They needed a specialist for drawing pictures as fast as possible. The seeds for the GPU were planted out of necessity. The first real glimpse of what dedicated graphics hardware could do didn't come from a personal computer. It actually came from the arcade. Back in the late 1970s and early 80s, arcades were, honestly, the pinnacle of gaming technology. While home computers were struggling to draw just a few colored blocks, arcade cabinets were delivering fast, fluid, and vibrant experiences that honestly felt like they were from the future. Games like Galaga, Pac-Man, and Donkey Kong were, well, just dazzling. And the secret sauce wasn't a super powerful CPU. Nope, it was custom hardware, a dedicated circuit board packed with chips designed specifically for graphics. These arcade boards were really the true ancestors of the modern GPU. They were built with a single purpose in mind: to handle the repetitive tasks of moving sprites around the screen, detecting collisions, and managing animations. By offloading these tasks from the main processor, the game could run faster and look way better. The main CPU would handle the game's logic, the rules, the scoring, the enemy behavior. while the specialized graphics chips would handle the visual output. This division of labor was, honestly, a game changer. It was the first mainstream application of what we now call hardware acceleration. Think about what made those games so compelling. It was the speed and smoothness of the action. In a game like Galaga, you had your ship, dozens of enemy ships, and all of their bullets on screen at the same time, all moving independently. A home computer of that era would have just choked trying to render that. It would have been a slideshow. But the custom arcade hardware could handle it all in real time. Each graphical element, or sprite, was its own object that the hardware could manipulate directly, freeing the CPU to just worry about the game's core intelligence. This arcade boom kicked off an arms race. Game companies like Namco, Nintendo, and Atari were constantly pushing the envelope, designing more powerful and more specialized graphics hardware to one-up the competition. They were basically creating single-purpose GPUs for each new game. These boards weren't programmable or flexible like modern graphics cards. They were hardwired to do one thing perfectly. But they proved a critical concept. If you want great graphics, you need dedicated hardware. And that was a lesson the personal computer industry was about to learn in a really big way. As personal computers became common, the demand for better graphics grew. Lessons learned in arcades began to filter down. IBM's first PC in 1981 included the monochrome display adapter, MDA, one of the first true graphics cards, though it only displayed green text. Color graphics adapter, CGA, brought 4 colors, then enhanced graphics adapter, EGA, brought 16. 1987's video graphics array, VGA, became the standard, enabling more sophisticated images and games. Graphics accelerators emerged, offloading tasks from the CPU with onboard processors, marking the true beginning of dedicated graphics processing. The mid-90s marked a turning point. 3D graphics exploded onto the scene. Games like Doom and Quake demanded more than CPUs could handle. Enter 3DFX Interactive, whose Voodoo card transformed gaming with smooth, immersive 3D visuals. Suddenly, every gamer wanted a Voodoo card. Meanwhile, ATI and a newcomer, NVIDIA, joined the fray. NVIDIA's Riva 128 combined 2D and 3D on one board, raising the stakes. The graphics wars ignited. New cards, better frame rates, and rapid innovation. In 1999, NVIDIA coined the term GPU with the GeForce 256. A chip with integrated transform lighting and rendering. This wasn't just marketing, it was a new era. The graphics card became a powerful programmable processor, setting the stage for GPUs to change the world. The first graphics war had begun, and the GPU was here to stay. CPUs are the brains, versatile, precise, and great at complex step-by-step tasks. Imagine a world-class surgeon, perfect for delicate operations but slow at moving mountains of sand. For that, you need an army. Thousands of workers, each doing a simple job in parallel. That's the GPU, not a genius but a force of numbers. CPUs handle your operating system and apps. GPUs tackle millions of pixel calculations at once. The CPU is the foreman, the GPU the workforce. It's a partnership, the generalist and the specialist, each excelling at what they do best. When you need speed and complexity, call the CPU. When you need brute force for repetitive tasks, unleash the GPU. That's why your computer needs both. Together they make modern computing possible. Picture a supermarket checkout. The CPU is a single superstar cashier. Great for complex orders, but a bottleneck when the store is packed. The GPU is 1,000 basic cashiers, each limited, but together, they clear the crowd instantly. CPUs excel at serial processing, one task at a time, lightning fast. GPUs thrive on parallel processing, thousands of simple tasks, all at once. CPUs give you instant response for everyday tasks. GPUs maximize throughput, perfect for graphics and AI. For problems split into thousands of pieces, the GPU's approach is unbeatable. That's the power of parallelism. It's why GPUs are revolutionizing more than just games. The secret is in the cores. CPUs have a handful of powerful complex cores. Think a small team of geniuses. Each core is packed with advanced logic and fast memory, built for versatility. But you can only fit so many on a chip. GPUs flip the script. Thousands of simple, specialized cores, each focused on math. No fancy logic, just raw calculation. By simplifying, GPUs pack in an army, 10,000 or more on a single chip. It's brute force over brilliance. This design gives GPUs their legendary parallel power. For tasks that can be split up, nothing beats a GPU's army of cores. That's why they're the backbone of modern graphics and AI. Why not merge CPU and GPU? In many devices we already do. Laptops and phones use chips with both, efficient, compact, and cost-effective. These APUs handle everyday tasks and light gaming without a separate graphics card. But for serious gaming or AI, you need a dedicated GPU, more power, more memory, more cores. Integrated chips share resources, discrete GPUs get it all to themselves. It's not about one being better, it's about the right tool for the job. CPUs and GPUs together unlock new possibilities. The real breakthrough? Letting each do what it does best, side by side. That's the secret to modern computing's power. Next, let's look inside the GPU itself. Imagine the GPU as a city, dense, organized, and built for one purpose: parallel work. Unlike CPUs, which have a few big government buildings, GPUs are packed with identical apartment blocks, the core clusters. These clusters, called streaming multiprocessors (SMS) by NVIDIA or compute units (CUs) by AMD, are like factory floors. Each SM contains a team of simple cores, a small local cache, and a scheduler. The GPU is a collection of these factories, all working in parallel. The CPU sends a big job to an SM, the SM breaks it down for its team. This hierarchy keeps things efficient and manageable. Instead of talking to 10,000 workers, the system talks to a few dozen managers. The result: massive workloads handled with ease. It's a masterclass in delegation and parallelism. That's how GPUs deliver their incredible performance. Let's zoom in on the streaming multiprocessor, or SM. This is the fundamental building block of the modern GPU. Inside each SM, you'll find processing cores and a special scheduler. The scheduler assigns tasks, called a warp, to the cores. A warp is a group of tasks executed in lockstep using a model called CIMT, making GPUs efficient for graphics and AI. The SM also has super-fast on-chip memory, allowing the cores to share data quickly, vital for performance. It's this integration that makes the SM the heart of the GPU's processing power. So we've gone from the city to the factory floor, and now let's talk about the individual worker. In NVIDIA's world, this is the CUDA core. In AMD's world, it's called a stream processor. For simplicity, let's stick with the CUDA core, but the concept is the same. This is the fundamental unit of computation. This is the tiny engine that does the math. It is the single construction worker with the shovel from our earlier analogy. It is simple, it is small, and there are thousands and thousands of them. A top-tier card like an RTX 4090 has over 16,000 of these little guys. What can a CUDA core actually do? Not a whole lot on its own. It's a specialist. Its main job is to perform mathematical calculations, specifically floating point operations, which are essential for 3D graphics and scientific computing. These are calculations that involve decimal points, which are much more complex than the simple integer math that CPUs often handle. The core can take two numbers, like 3.14 and 2.71, and multiply them together. That's its bread and butter. It's designed to be a lean, mean floating point math machine. The beauty of the CUDA core is its simplicity. It lacks all the complex, sophisticated features of a CPU core. There's no fancy branch prediction or out-of-order execution. It's designed to be a follower. It waits for the SM scheduler to give it an instruction, it executes that instruction on its piece of data, and then it reports the result. This simplicity is a feature, not a bug. It means the core uses very few transistors and consumes very little power compared to a CPU core. This is what allows engineers to cram so many of them onto a single chip, creating that massive parallel army. So when you hear a graphics card has 10,000 cores, it's important not to directly compare that to a CPU's 16 cores. It's an apples to oranges comparison. A single CPU core is a genius generalist, a single CUDA core is a hyper-specialized worker bee. The CPU's power comes from the capability of its individual cores, while the GPU's power comes from the sheer, overwhelming number of its cores working in perfect unison. It's this massive quantity of simple processors that gives the GPU its incredible throughput for tasks that can be split into thousands of identical pieces. VRAM, or video RAM, is the dedicated memory on a graphics card. Unlike system RAM, VRAM is high-performance memory designed to feed the GPU's cores with data quickly. Think of VRAM as a massive superhighway leading directly to the GPU. Its key feature is bandwidth, measuring how much data moves at once. A wide memory bus creates a superhighway for data. This high-bandwidth memory is crucial for AI, enabling rapid data movement between cores and memory. The VRAM superhighway is as vital as the cores themselves. So we have the cores, the SMS that organize them, and the VRAM that feeds them. But what are they actually doing? Originally, the cores on a GPU were highly specialized. There were different types of cores for different parts of the graphics pipeline. Vertex shaders for handling 3D model geometry, and pixel shaders for coloring the individual pixels. A vertex shader would calculate a triangle's position in 3D space, and then a pixel shader would calculate the color of each pixel inside that triangle. This was a fixed function pipeline, efficient but inflexible. The big revolution came with the invention of the unified shader. Around the mid-2000s, companies like NVIDIA and ATI, which is now AMD, realized it would be much more flexible to have a single, programmable type of core that could perform any of these tasks. Instead of having dedicated hardware for vertices and pixels, they created a pool of general-purpose programmable cores, the ancestors of today's CUDA cores. Now the GPU's scheduler could dynamically assign these cores to whatever task was needed most at that moment. If a scene had very complex geometry, more cores would act as vertex shaders. If it had complex lighting, more would act as pixel shaders. This programmability was the key that unlocked the GPU for general-purpose computing. Because the cores were no longer hardwired for just graphics tasks, developers could write their own custom programs or shaders to run on them. A programmer could now write a shader that, instead of calculating a pixel's color, could simulate fluid dynamics or calculate financial risk models or, most importantly, perform the matrix multiplications at the heart of an AI neural network. The unified shader architecture turned the GPU from a specialized graphics tool into a massively parallel programmable supercomputer. This is where NVIDIA's CUDA platform came in. CUDA, which stands for Compute Unified Device Architecture, provided a programming language and a set of tools that made it much easier for scientists and researchers, not just graphics programmers, to tap into the immense power of these unified shader cores. They no longer had to pretend they were rendering a triangle to trick the GPU into doing their math. They could now directly program the GPU to solve their general-purpose parallel problems. This decision to open up the GPU's programmable architecture to the world was the final critical step that paved the way for the AI revolution. This incredible hardware built for video games has thousands of simple cores and a super-fast memory highway. But a few smart people in AI noticed its potential to build a brain. This discovery was almost an accident. Training neural networks required repetitive matrix multiplication. It was simple, repetitive, and massively parallel. This was the light bulb moment. They could trick a GPU into doing their work. Suddenly, a process that took months could be done in days. The GPU, the accidental hero, had given AI the superpower it needed. To understand why GPUs are a perfect match for AI, you need to grasp the basics of neural networks. These AI models are inspired by the human brain, with billions of interconnected neurons. Artificial neural networks mimic this, using layers of digital neurons and weighted connections. Training involves adjusting these weights through countless examples, like showing it thousands of cat pictures. This process relies heavily on matrix multiplications, a type of math GPUs excel at. Unlike CPUs, GPUs can perform these calculations simultaneously across thousands of cores. This makes GPUs ideal for the repetitive parallel math needed for AI training. It's a perfect match of hardware and software. In 2012, everything changed with the ImageNet competition. A team from the University of Toronto entered AlexNet. It destroyed the competition with a shocking leap in accuracy using NVIDIA GPUs. This was the big bang for the modern AI revolution. Suddenly, every major tech company pivoted, realizing GPUs were the future. The demand for GPUs exploded, kicking off the deep learning boom. It reshaped the entire tech industry. After the AlexNet moment, the floodgates opened. GPU-powered deep learning is now applied to almost every problem. Consider AI art generators like Midjourney or DALL-E. This technology also powers chatbots like ChatGPT and Google's Gemini. In medicine, GPUs analyze medical scans, helping doctors spot diseases earlier. The brain of a self-driving car uses GPUs to process data and make driving decisions. GPU-powered AI is everywhere, enhancing countless products and services. This absolute dependency on GPUs for building cutting-edge AI has created a new kind of global arms race. But instead of missiles and tanks, the world's biggest tech companies are stockpiling graphics cards. The ability to train bigger and more powerful AI models is now directly tied to how much compute you have access to, which really just means how many high-end GPUs you can get your hands on. This has turned GPUs, especially the high-end data center models from companies like NVIDIA, into the most sought-after resource in the tech industry. They are the new oil, the new gold. Companies like Google, Microsoft, Meta, and OpenAI are spending billions upon billions of dollars to build out their AI infrastructure. They are constructing massive data centers, the size of multiple football fields, filled with nothing but tens of thousands of GPUs all networked together. These are essentially AI supercomputers, and the competition to build the biggest and the best is incredibly fierce. The company with the most compute has a significant advantage. They can train more complex models, experiment faster, and ultimately build the next generation of AI that could define the future of technology. This insatiable demand has had a massive ripple effect across the entire industry. It has catapulted GPU manufacturers, particularly NVIDIA, into becoming one of the most valuable companies in the world. It has created supply chain bottlenecks and shortages, as everyone from university researchers to entire nations tries to secure these precious chips. We're now in an era where a company's power and potential are literally measured by the number of H100 or B200 GPUs they own. Access to compute has become a geopolitical issue, with governments viewing AI capabilities as a matter of national security and economic competitiveness. This gold rush is a testament to how central the GPU has become to our technological future. It's a piece of hardware that started as a way to make games look better, and has now become the foundational engine for one of the most transformative technologies in human history. The race for compute is really a race for intelligence itself, and as we look forward, the continued evolution of these powerful parallel processors will not only shape the future of AI, but will also redefine what's possible across every industry and every aspect of our lives. The revolution is here, and it's being processed in parallel. So, where do we go from here? We've seen the GPU's incredible journey to the undisputed engine of the AI revolution. It's clear that we are likely just getting started. The demand for more powerful, more efficient parallel processors is pushing companies to innovate at a breathtaking pace. We're going to see GPUs become even more specialized for AI workloads. This trend will only accelerate. This relentless hardware improvement will unlock new frontiers in artificial intelligence. This power will also shrink, bringing powerful AI processing directly onto our personal devices. Your devices will become truly intelligent companions. When you step back, the GPU is more than just a component. It has become a catalyst for progress, changing discovery and creation itself. In science, it's enabling us to simulate complex systems. In creative fields, it's empowering artists with incredible new tools. The GPU is democratizing creation, giving individuals the power of an entire studio. From pushing pixels to powering the future of intelligence, it's a fascinating story. The GPU is the quiet engine making our intelligent future a reality. Imagine what we will build next. The future is parallel.